Hello everyone. In this video, I will discuss how trigonometric relations are useful in integrating some algebraic integrals involving the expressions square root of x squared plus a square, square root of x squared minus a square, and square root of a squared minus x squared. So if you have these algebraic expressions in some integrals, we can integrate those integrals using some trigonometric relations, and this method is known as trigonometric substitution method. So depending on what expression we have an integral, we will make a special type of trigonometric substitution. So I have made a table in which there are different types of expressions and which illustrates what kind of substitution you need to make in each case. For example, if you have something like square root of x squared plus a square in an integral, then we create this triangle. So where x is your uh, x is your one leg and a is your another leg of a right angle triangle, and you got hypotenuse is equal to square root of x squared plus a square. So if you construct this triangle and let's say phi is the angle, so then we can see that x over a, from here you can see that x over a is, so it's your perpendicular over adjacent, so altitude over adjacent, so that would be tangent phi. And in this case we get x is equal to a tan phi, and we can take the differential of this. You get dx is equal to a secant square phi d phi, and similarly if you plug in the value here, so you will get square root of a square tangent square phi plus a square is equal to, so you can take a square common, so you get tangent square phi plus 1, which gives you a secant phi. Thus, if you just start with this substitution, you get everything else in here. So we replace all the quantities of the integral. So if you have x, dx, and square root of x squared plus a square, so you replace them by in trigonometric form and then solve the resulting new integral using one of the trigonometric identities method that we have discussed in the previous video. So similarly, if you have an expression of the type square root of x squared minus a square, then we construct this triangle, because by Pythagoras we knew that x should have been the biggest side. So x is this, then another one is a, and the third one would be x squared minus a square. And depending on this construction of the triangle, we get that x should be equal to, so we figure out what x should be equal to. So x should be equal to a secant phi, and we start with this substitution. We find the corresponding dx, and similarly when you put x equal to a secant phi here, you get this algebraic expression equals to a tangent phi, and we replace everything in the integral in terms of trigonometric quantities, and then we solve the integral. Lastly, if you have something of the form uh, square root of a square minus x square, so in that case, as the name suggests, so a should be the biggest side, so we construct this triangle, and then x is the other leg, and we get square root of a square minus x square, and we start with the substitution x is equal to a cosine phi, and then we find the differential, and also we change everything inside the expression, and again we use our identities method after this step. So this is a little bit of a summary of what we do, like how we do the trigonometric substitutions. So one thing I would like to mention that of course in these triangles, so since two legs can interchange with each other, so there might be like instead of having x equal to a cosine phi, you could have x equal to a sine phi. So it would work. So depending on how you construct your two legs. So in the next table, I have summarized even further like what to do. So if you have an expression of the form square root of x square plus a square, so we start with the substitution x is equal to a tangent phi or any angle tangent theta, whatever you want to call it. And then we use this identity 1 plus tangent square phi is equal to secant square phi. And then we rewrite our square root term as a secant phi. So this is just a bit of summary. So if you have expression square root of x square minus a square, you do the substitution x is equal to a secant phi. Similarly, if you have square root of a square minus x square, you do x equal to a sine phi or a cosine phi. And based on that, you use the identities and you solve your integral. So I'm going to do a few examples in which I'm going to solve these methods one by one. So then it will be more clear that why we do a substitution and how we do it. So let's take a moment to read the next example. So you can pause this video and read the next problem. So in this example, we are given that the end effector of a robotic arm moves back and forth along a curve from 1 centimeter to 4 centimeters, and the distance that d that it moves in one cycle is given by this integral. So we need to find the distance d. One thing that I want to point out is that so arc length along a curve, so general formula is integral from a to b of square root of 1 plus slope square dx. So that is the general formula for arc length. So in this case, we are already given the formula. So we need to find distance d. So first of all, we will find our dy over dx for our given curve 3 ln x. Since y is equal to 3 ln x, so dy over dx should be 3 over. So putting the value in the expression of d, we get so square root of 1 plus, so dy over dx is 3 over x square dx. And then we see that inside the square root we have 1 plus 9 over x square dx, and we can take the common denominator and our integral becomes, so here we get x squared plus 9 over x squared, so common denominator, right? So we get this. And now we notice that in this integral we have this expression x squared plus 9, square root of that. So which is like square root of x squared plus 3 squared. So which is of the form square root of x squared plus a squared. So this tells us that in order to solve this, we should use our substitution x is equal to a tangent phi or x equals to a tangent theta. So we're gonna use the substitution x is equal to a tangent theta, because the triangle that we're gonna create in this case is, so we have 90-degree angle, so this angle is theta. So our hypotenuse is x squared plus 9, which is x squared plus 3 square. So one of the legs gonna be x, another leg is gonna be 3, and from here we get x equals to 3 tangent theta. So that would be our substitution in this case. So since we have to make this substitution in this integral, so we need the value of dx, and we also need the value of square root of x squared plus 9. So in this case, from the triangle, you can see that square root of x squared plus 9 would be 3 secant theta, and also the differential would be 3. So tangent theta is secant squared theta d theta, and square root of x square plus 9. So that would become 9 tangent square theta plus 9. So 9 tangent square theta plus 1. So which becomes 3 secant theta. So we're going to do all these three substitutions in our given integral. So what I'm going to do is, since this is a definite integral, so I'm just going to uh, first evaluate the indefinite integral, and in the end I'll plug back the limits. So I'm going to call this my number 1, and I'm going to first evaluate my indefinite integral x as square root of x squared plus 9 over x. So when I do the substitution here, so I notice that I get, so square root of x squared plus 9 is replaced by 3 secant theta. So x is replaced by 3 tangent theta, and dx is replaced by 3 secant square theta d theta. 3 secant square theta d theta. So here we notice that 3 and 3 cancels, and we are left with, so 1 3 here, and we are left with secant theta over tangent theta secant square theta d theta. And now I'm going to write this secant square theta. I'm going to use the identity that secant square theta is equal to 1 plus tangent square theta d theta. So in the next step, we notice that we can split this into two integrals. So we get 3. So secant theta over tangent theta d theta would be our first integral, plus integral of secant theta tangent square theta over tangent theta d theta. And secant theta over tangent theta can be written as, so if we just do a bit of simplification, we see that this is 1 over cosine theta, and this is sine theta over cosine theta. So cosine theta gonna get cancelled, and we're gonna left with 1 over sine theta, which is equals to cosecant theta. So our first integral becomes, oh, so remember this 3 is with both integrals. So our first integral becomes integral cosecant theta d theta, and in second integral tangent gonna get cancelled, we get integral of secant theta tangent theta d theta. So now we see that we know the integral of these. So integral of cosecant theta is ln mod cosecant theta minus cotangent theta, plus integral of secant theta tangent theta is secant theta, and since this was indefinite integral, we're gonna write plus c. So now don't forget to convert this back into the original variable, and then we can use our limits. So our original variable was x, so let's try to plug in all the values in terms of x. So using this triangle, so we see that sine theta is x over square root of x squared plus 9. So if you want cosecant theta, that should be square root of x squared plus 9 over x. Similarly, we need the value of cotangent. So cotangent theta would be inverse, will be reciprocal of tangent. So that would be 3 over x. And secant theta would be the reciprocal of cosine. So secant theta would be square root of x squared plus 9 over 3. So you get all these values using your triangle information, and we plug in here. Thus we get 3 times ln of, so cosecant is square root of x squared plus 9 over x minus 3 over x, plus secant is square root of x squared plus 9 over 3, and plus c. So this was our indefinite integrals. We haven't included the limits so far. So now let's go back to our original problem. So our original problem was to evaluate this integral. So from number 1, so let's try to plug in the values of x from 1 to 4. We get, so using this in 1, we get, so 3 times 2 is 6, and then I'm going to rewrite this whole integral that we have evaluated here. So we get ln of, so this whole integral from, so limits from 1 to 4. So let's plug in our limits. So we put the value 4 and 1 here. So upper limit minus lower limit. So I put 4 here and then I put 1 here. Similarly, for the second term, we get square root of 16 plus 9. So square root of 25 over 3 minus square root of 10 over 3. And in the next step, we notice that we got 6 ln, so 5 minus 3, 2 over 4. So this is 0.5 minus ln of square root of 10 minus 3 plus 5 over 3 minus square root of 10 over 3. And we can use the calculator to figure out this value, and in the end we get approximately 10.4 centimeter. So that is the required distance which the robotic joint moves in one cycle. Let's try a couple of few examples in which we use the other trigonometric substitutions. So in this one, we can see that we have something of the form x squared minus a squared, because square root of x squared minus 16 is of the form x squared minus 4 squared. So a is 4 in this case. And when we have square root of x squared minus a squared, so this form of expression, so we start with our substitution, x is equal to a secant theta. So we use substitution x equal to a secant theta. So in this case, we will use x equal to 4 secant theta. Get the corresponding triangle, we will see that, so x squared, so that x should be the hypotenuse and the other sides can be 4, and square root of x squared minus 4 squared, which is x squared minus 16, square root of that. So using our substitution, so dx should be 4 secant theta tangent theta d theta, and also square root of x squared minus 16 should be equal to 4 tangent theta. So our integral becomes, so integral of square root of x squared minus 16 is 4 tangent theta over x cube, which means 4 cube secant cube theta, and dx is 4 secant theta tangent theta d theta. So if we do a little bit cleanup here, so we see that in the end we are left with, so tangent square theta over secant square theta, so this can be written as sine square theta over cosine square theta. Similarly, for 1 over secant square theta is cos square theta d theta, and cos square cancels, and we are left with 1 over 4 sine square theta d theta. And now we know that in order to solve this integral, we can use the trig identity that sine squared theta is equals to 1 minus cos 2 theta over 2. So using this trig identity, we get 1 over 4 integral of 1 minus cosine 2 theta over 2. So I'm just going to split this into two integrals. d theta. So we got 1 over 8 integral of d theta minus 1 over 8 integral of cosine of 2 theta d theta. So in this case, so this would be simply 1 over 8 theta. And here, in order to make, so if you have 2 theta as your u and you want to make the differential of u, so that it means we need another 2 here. So we need to divide by 2. So we got integral of cos u du, so which should be sine u. So in other words, which should be sine of 2 theta. So we got 1 over 16 sine of u or sine of 2 theta plus c, since this is our indefinite integral. So in the end, we put back everything in terms of x. For that, we can use our triangle 4 over x. So it means theta should be cosine inverse 4 over x. Thus, for the first part, we got 1 over 8 cosine inverse 4 over x. And for sine 2 theta, we can use the identity that sine 2 theta is equal to 2 sine theta cosine theta, and we can plug in the value of sine and cosine here. So sine using this triangle would be square root of x square minus 4 square or x square minus 16 divided by x, and cosine theta is 4 over x. So this is the value of sine 2 theta. So we use the identity. So let's plug in this value here and we get 2 times, so square root of x square minus 16 over x, 4 over x, and plus c. And in the end, we get 1 over 8 cosine inverse 4 over x. And we can do some cancellation here. So we get negative 1 over 2 square root of x square minus 16 over x square plus c. So that is your required answer. So it's very important that whenever you do a trigonometric substitution, in the end, don't forget to convert everything back in terms of original variable. Let's do one more example. So we are given this, that find the integral of square root of negative x squared plus 4x plus 5. So our intuition says that we should make it look like square root of a square minus x square, because here we have negative in front of x square. It means we need to take help of complete the square method first. So in order to complete the square, so this should look something like x plus some number whole square plus d. So I'm not using a and b here because we already have a here, so that we don't mix it with this a. So I'm using c and d as my numbers. So what we're going to do, we're going to expand this right hand side, and then we're going to equate the like terms, the coefficient of like terms, and we can figure out our value of c and d. So x squared plus 2cx plus c squared plus d. So we get negative x squared, negative 2cx, and for the constant term we got negative c squared plus d. And on this side we have negative x squared plus 4x plus 5. So now equating the coefficients of like terms, so coefficient of x is negative 4 on this side and negative 2c on this side. We get negative 4 is equal to 2c. So this implies c should be negative 2. Similarly, if you compare the constant terms, so negative c squared plus d should be equal to 5. and c is -2, so -4 plus d equal to 5. So this implies d should be equal to 9. Thus, by comparing our square, so -x squared plus 4x plus 5 becomes equals to -x plus c, which is x minus 2 square plus 9. So this is our completing the square. Thus we can see that our given integral is of the form, so 9 minus x minus 2 whole square dx. So this is of the form a square minus x square, square root of that. If you want, you can use the substitution u is equal to x minus 2. So du should be dx. So our integral becomes 9 minus u square du, and which is of this form. And now whenever we have this form, we use our trig. So we can use the trig substitution, x is equal to a sine theta or x equals to a cosine theta, depending on how you draw your triangle. So let's say here we have 3 and u as our sides, and then we get 9 minus u square, square root of that. So in this case, we can clearly see that, so if you get u over 3, that would be equal to cos theta. So we can do the substitution. So let u is equal to 3 cosine theta. This implies du would be equal to -3 sine theta d theta, and square root of 9 minus u square would be 3 sine theta. So we're gonna use all this here. So our integral changes to integral of, so in place of square root of 9 minus u square, we get 3 sine theta. In place of du, we get -3 sine theta d theta. So thus we get, so 3 times 3, so -9 outside, inside we have sine square theta d theta. Now we can use the identity that sine square theta is equal to 1 minus cos 2 theta over 2, which is half, minus cosine 2 theta over 2. So we can write this integral as -9 and then 1 over 2 minus cosine 2 theta over 2 d theta, or even we can take 2 out, so we get -9. So integral of 1 minus cosine 2 theta d theta, or in other words, we get -9 over 2 integral of d theta minus integral of cosine 2 theta d theta. So -9 over 2 theta minus integral of cosine 2 theta would be sine 2 theta over 2 plus c. So we get -9 over 2 theta plus 9 over 4 sine 2 theta plus c. So don't forget, in the end, we need to plug back everything in terms of original variable, which was x. So since we did the substitution twice here, so we did u equals to this, and then we had x before. So we have to back substitute twice. So in this case, we get, so -9 over 2, and we can use our triangle to figure out the value of theta and sine 2 theta. So since we have cosine theta equal to u over 3, so theta should be cosine inverse u over 3. And for our sine 2 theta, we can use our trig identity. So sine 2 theta is equal to twice sine theta cos theta. So value of cos theta, we already know u over 3, and value of sine theta would be square root of 9 minus u square over 3. So using the values here, so theta is cosine inverse u over 3, and we have 9 over 4, and in place of sine 2 theta we write this value, so we get 2 times square root of 9 minus u square over 3, u over 3 plus c. And we see that we get negative 9 over 2 cosine inverse u over 3, and here 3 times 3, so 9 is cancelled, and then we get 2 here, so we get plus 1 over 2 u times square root of 9 minus u square plus c. But since u was not our original variable, we also made a substitution that u equals to x minus 2. So let's plug in u equals to x minus 2. So using that, we convert back into our original variable, and we get negative 9 over 2 cosine inverse x minus 2 over 3 plus half x minus 2 square root of 9 minus x minus 2 square plus c. So this is our required solution. So based on what a kind of algebraic expression you have, you can use the suitable trigonometric substitution. And the main thing is, don't forget to plug back everything in terms of the original variable. I hope you enjoyed this video, so keep watching my videos for the other methods of integration. Thanks for watching.